Well, hello, and welcome to Wise Up on Air. I'm Damian Kastbauer. I'm the software product manager here at Audiokinetic, and you are in for a treat today because we are going to go deep into CPU and performance improvements in the next full release of Wwise 2022.1. This is going to be a fun ride for folks who are interested in going all the way to runtime with Wwise and getting a better understanding of a lot of the mechanisms in place and how Wwise works really under the hood. So thanks for tuning in. We're glad to be here today. And if these kind of things are interesting to you, you'll want to mark the calendar for next Wednesday. We'll be hosting our annual Wwise Worldwide Online Expo. That's next Wednesday the 12th at 2 p.m. Eastern Time, 11 Pacific. This is going to be a cool product-focused live stream. We're going to have a bunch of special guests on, and we'll also have a very exciting Audiokinetic product announcement. So you'll want to get signed up and registered for that. We're going to drop the registration link into the description for this live stream as well as into the chat here. So stay tuned for that. It's going to be exciting, and we can't wait to talk more about what is happening at Audiokinetic. And speaking of that, we're here today with David Crooks, software developer here working on the core engine team. Hey, David. Good to see you today. And you're going to take us on a journey all the way to the core of the Wwise engine. But give us a little bit of background. Tell us about your role at Audiokinetic and, how you arrived.
And working on like stability for that, performance improvements for that. As mentioned, we do a lot of first line support, or second line support really. As of later, last few years, it's also been working on a lot of the new platforms that have come online, like PS5, Xbox Series X, and all that kind of stuff. And that's where I've been spending a lot of my time, is performance issues, especially for the new platforms, and trying to get what we can out of them. Especially because they both involve a lot of really high-end audio now, as I think most people know by this point.
Exactly. And one of the things I've always seen you in your role as a software developer on the core team as really having a keen eye for is that performance side of things. And with the increasing capabilities across platforms, we're always squeezing as much out of these different platforms and making sure that Wwise is optimized to run across all of the different platforms we support. So it's a big task that core team that you're part of is, shouldered with the responsibility of providing that stable and performant experience. So I'm excited to dig right in. Should we jump in?
Yeah, certainly. As we do, one thing I will note is, as Damien has alluded to before, like this Wwise Up on Air might be a bit different from what you're used to, because we're not going into many details about the authoring tool. This is much more focused on like the SDK integrations for the runtime, and much more programmer focused. So certainly, if you're not already an audio programmer in the chat already, and you're an audio designer on a team that has their own programmers, might want to ping them to at least get them into the chat now, or they can catch the VOD later, of course. But this is much more focused on like code and code integrations than it is just on the design side of the authoring tools.
Yeah, and as you mentioned, having them here or having folks here participating, feel free to put any questions that come up during the presentation into the chat. It's especially a great time to engage, and we'll weave those questions in when we can throughout the presentation and throughout this conversation. So we would love to get your perspective. If there's something that's not quite connecting, there's a good possibility that if we can help connect those dots in real time, that it will benefit anyone who tunes in. So thanks for that. And with that, take it away, David.
So, as mentioned, this presentation is mostly going to be focused on the SDK runtime performance improvements we have in Wwise 2022.1. As mentioned, I'm David Crooks, one of the software developers at Audiokinetic on Wwise. So for this presentation, I'm going to be going over some performance improvements highlights that we have for this version. Go over some of the details we have on improvements to our CPU profiling, and also some of the ways that we revamped the CPU scheduling that is available in Wwise. So first, the general performance improvements that we have in 22.1. So one thing that many developers using Wwise have definitely felt is the issue of RTPC updates becoming disproportionately expensive as projects tend to grow in size. To the point that a lot of developers have tended to use a variety of workarounds to try to achieve satisfactory performance in their game, mostly just to try and reduce how many RTPCs are loaded or reduce the number of game objects active in Wwise at one time. For example, this can take the form of aggressive culling of game objects before posting an event, or having to manually preclude sounds that are considered inconsequential without being able to rely on Wwise just converting voices to virtual on its own and having the voices be really, really cheap to process. So addressing RTPCs was one of the big objectives that we had for 22.1. I will note the behavior of RTPCs was kept intact, so there should be no changes required. This is just a straight performance improvement. So whenever Wwise processed an RTPC change, Wwise would have to check for each active RTPC user and determine if that RTPC update was relevant for the game object, and typically each game object would have multiple subscriptions attached to that. Typically, this meant that things like RTPCs updating based on relative positions would invoke a quadratic cost and complexity. Now in 22.1, much of that work is skipped, and RTPC updates should have a more predictable update cost because we have determined the list of relevant RTPCs ahead of time when the sound bank is loaded. This should drastically reduce the amount of time spent on RTPC updates and make their performance more predictable. If you're one of the developers that did a lot of aggressive pre-culling of game objects for this reason, it may be worth investigating if that is still required anymore, or if not, maybe you just enjoy the performance improvements as is. Next, we have some improvements to the built-in low-pass filter and high-pass filter in the voice pipeline. These are really common operations, as a lot of designers tend to apply LPF or HPFs to many voices or incorporate them as a part of their mixing to audio buses or aux buses, typically as a part of attenuation curves. And to be clear, we're talking about the LPF and HPF that you would see in the voice graph here. This operation tended to be a really big CPU hotspot that I think many developers who have done instruction sampling profiling of their game as a whole, let alone just focus on Wwise, would tend to see these LPF and HPF processing updates come up as a hotspot even then. So in order to address this, we've rewritten a large portion of our audio processing pipeline that handled the core mixing and filtering. A particular emphasis was put on the fact that many developers are using these features on many voices at a time, dozens or possibly hundreds, and also that LPF and HPF tend to be used together. And then also by taking the design of modern CPUs into consideration, be it PC, consoles, or even mobile CPUs, actually. Modern Apple Silicon and ARM Cortex chips also reap significant benefits from the improvements that we've done for this process. At least when comparing Wwise 2021.1.0 versus 2022.1.0, on last generation consoles, we measured about a 2x improvement in throughput performance. Whereas on current generation consoles across the same versions of Wwise, we measured a 5x improvement in throughput, up to a 5x improvement in throughput performance. In particular, for any developers who were focused on last generation development on 21.1 or earlier, and are now moving to focus on current gen development on 22.1, we expect up to a 10x improvement of throughput performance of this feature. So that makes it just a very, very cheap operation compared to what it might have been before. We also have some good improvements to spatial audio performance. Two of the big highlights here are that diffraction edges for spatial audio are now discovered by tracing rays through the world, whereas before the diffraction edges were discovered by a very exhaustive inspection of all the geometry in the scene. So that should help make that performance a lot more predictable and lower. And as well, diffraction performance now has a much lower and fixed overhead per emitter. And that's scalable based on the number of rays and order of diffraction available. As well, spatial audio jobs can now be time sliced across multiple sound engine ticks to try and mitigate CPU spikes that can come up because of that. And that's configurable in the AK spatial audio initialization settings. And one of the operands for this is that, or one of the techniques used for this is that a priority queue does ensure that latency sensitive operations are still performed early across those jobs. So things like playing new sounds or changing active rooms should still be very responsive, even though that load is balanced across multiple audio ticks. Lastly, we have some other smaller highlights to come either as a part of Wwise 2022.1 or were released during the patch releases for Wwise 2021.1 that I want to call out. For one, the AK compressor and AK expander effects were rewritten with throughput performance improvements of up to 4x in many scenarios. But for ambisonics, the improvement is magnified even further with over 20x improvement compared to 21.1.0. One other related benefit that we had in that rewrite is that we also addressed some inconsistencies in behavior across different channel configurations for these effects. So if you had any adjustments in your mix when targeting certain channel accounts or using 3D audio that were related to these two effects, you can probably remove those now. Like just everything's just a lot more consistent. Sorry. Next, the AK convolution effect with hardware acceleration enabled and WEM opus decoding with hardware acceleration enabled can now be processed fully asynchronously. This eliminates much of the CPU time spent on these features, making them even cheaper than they were before. Of course, these are only applicable for certain platforms that support these capabilities, so please check your platform-specific documentation for more details about these elements. And lastly, Wwise has a debug feature in the initialization settings called debug out of range check, which itself is not new. For those not familiar, it's a useful tool to track down where erroneous values such as infinities or not numbers or just really loud volumes are being introduced in the voice pipeline. The reason why we want to call this out, though, is that this feature runs much, much faster than it did before. There is still a mild hit to performance, but now it's only a 10 to 15% increase in sound engine execution time, as opposed to what it was before, which where it would like triple the amount of time it took for the total sound engine to run. One benefit of this is that it might be low enough that maybe you could keep it on all of the time for your development builds to try and address or catch these problems much sooner than they would otherwise, without much of an impact on your developer experience when doing sound design or just other things in the game.
Awesome overview, David. And exactly what we're here to talk about today is just all of the great work that goes into tooling Wwise, both for speed, performance, and stability. I just wanted to plus up a couple of things that you were talking about there. You kicked it off talking about RTPC performance. And one of the ways that folks can see that manifested is in the GameSyncs monitor when you're profiling RTPCs connected to a game. You have a lot more opportunity to leverage these real-time parameters because of how how optimized they are now. And that game syncs monitor gives designers a view into understanding those game parameters coming from the game. So just a cool tie-in there for folks who are looking at Wwise through the lens of the profiler when they're connected to their game. Uh, you know, those game parameters are there to use, and anytime you can grab dynamic information from the game to make your game better and more responsive and synchronous with what's happening on screen, we just want to give you all of that control and power to leverage those. The other thing you were talking about were those filter improvements. And another authoring facing feature coming to 22.1 is the global filter behavior that we added to the project settings in the project to be able to change the way that those global filters are measured across your project. So if you're looking for more information on that, you can jump over to our blog. We've got a What's New for 22.1 to give you more information about that global filter behavior. And then lastly, I'm just reiterating what you said about spatial audio load balancing. And, spatial audio is one of these technologies that really benefits games that take advantage of it. And this ability to load balance and scale it based on the availability of resources is something that we, again, are continually moving forward in order for people to take more advantage of that technology. So thanks for that overview, and I'm edge of my seat to dive deep into the improved CPU profiling. Thanks.
Yeah. And just to highlight, like some of the performance improvements that we have allows those features that Damien described to be much more practical and available for developers to use, if not in more cases, at least at a larger scale. So that helps maybe drive that as well.
Yeah, exactly.
Now, so those were what we described were all just like the raw CPU performance improvements that you get out of the box. Hey, just Wwise just runs faster with the new version, hopefully. I think we've done the job, but just to make sure. But in addition to this, we were also delivering some improvements to CPU profiling to help give developers more actionable information when investigating CPU performance. The biggest part of this are new callback functions that we have added in the SDK. These are FN profiler push timer, pop timer, and post marker. Push timer and pop timer are the most major ones because these are used to provide timer scope information on when certain events start and stop inside of a Wwise frame. Post marker is used for some other noteworthy events, but are only used for noting voice starvations and audio frame boundaries right now. Push timer and pop timer, though, are to be used to add more detailed timing data to your CPU profiler of choice, whether it's Superluminal, RAD telemetry, Unreal's timing insights, or the tools provided as part of your platform SDKs, or just whatever your bespoke tools for your game engine are. We have some example integrations with platform tool sets provided in the Wwise SDK to demonstrate the functionality and how to set these hooks up. For example, you can see in the bottom right here, like this is what it looks like for integration with Pix for Xbox. So we hope that having this information available in your profiling tool set can be used both for audio programmers and non-audio programmers to better understand and inventory where the CPU time inside of Wwise is going without having to modify the sound engine or just rely on program counter sampling to get a clue as to where time is being spent. These new timer scopes are used not just for integrations with external tools, though. This data is also included in Wwise profiling sessions now as well. I'll note that this is currently for advanced users only and requires a hidden setting to enable. If you want to try out this tool for yourself, feel free to ask us for more information, but do note this feature is in an early state and it's not extremely polished compared to the other tools available. But even as is, it's still very useful to understand the Wwise CPU usage inside of Wwise authoring itself. But even without that in mind, it does provide the same data as the SDK profiling features, but comes with one extra cherry on top. And that is it provides extra attribution of timer scopes to specific voices and buses. In this way, it is possible to understand, not just broadly speaking, what effect is being costly, but pinpoint directly back to which bus or voice is being costly. Of course, this is also in addition to other capabilities such as correlating the CPU timing data for a certain tick with other aspects of Wise's profiling, like being able to see the CPU usage and the voice graph of a given tick side by side. On this diagram on the right here, you probably can't see it very well, but this shows that we have some bus tasks here, and it specifically calls out, oh, it's the room bus that has some cost to it, and it's the Wwise Room Verb plugin that is dominant in that CPU time there.
Cool. And kind of what I love there is that the profiling in Wwise is such a clear window into what's happening at runtime. And as a designer, like being able to understand that and be a good citizen across the project to be able to manage resources allocated for audio is a huge thing to have on your side. And now we're taking those tools even further into the runtime understanding, and will continue to evolve in that direction so that audio can always be a good steward across the development.
Yeah. And again, also be able to do things like answer the question of Wwise is reporting 80% CPU usage, but in my plugins, I only see 20%. Where's the other 60% going? This tool is what lets you answer that question inside the Wwise authoring tool itself.
Yeah. So we're going deeper and deeper under the hood here, and you're just you're doing a great job. Keep going.
Yeah. So now to talk about a more subtle but still really valuable issue for Wwise to deal with, and these are improvements to how Wwise schedules its CPU usage. So, and gets into like real heavy multi-threading territory, by the way. So hold on. So early on, when Wwise was developed, it was largely from a system on a thread era of game development. Games had relatively few threads and were not yet taking significant advantage of multi-core CPUs. And in this way, Wwise could run relatively fine. It would have its own thread that would periodically wake up and be relatively unobtrusive to the game frame. Either there were too few threads to fill up the CPU, or the threads could be moved around on the fly without much of an issue. However, since then, many games have significantly involved how they use the CPU. Most often, it is executing work as tasks or jobs on a pool of reusable worker threads as a task scheduler or job manager. In this way, many individual systems in the game can run piles of work asynchronous to and concurrent to each other as smaller jobs. It's a very flexible, scalable, and performant pattern for achieving great CPU utilization. And I think it'd be easy to say that most large scale games are doing something like this now. But Wwise is still running on its own freely scheduled thread, in addition to these worker threads, which can cause some performance frustrations. Let's consider a CPU timeline that a game might have. The main game thread here is split into multiple stages, but whenever it kicks its pre-fizz anim and post-fizz anim work, it's able to spread the work across an arbitrary number of CPU cores. Then, in order to proceed through the main thread, each of those jobs needs to finish before continuing. Specifically, the game frame cannot continue until all of those anim jobs are completed. If Wise's event manager thread, where we run all the sound engine processing, slips in to do some work and causes one of the worker threads to be unscheduled here, it's a little bit worse because one of the threads can't do the post-fizz anim job, But even then, it's still manageable. Like that job will be picked up by another core, and it'll just take a little bit longer. Everything still completes in a reasonable amount of time with only a mild hit to performance. However, it is occasionally the case where something like this would happen instead. In this case, Event Manager got woken up and got scheduled in the middle of execution of one of the pre-fizz anim jobs. As a result, the worker thread has been unscheduled from the CPU and cannot make any forward progress until Wise has completed its execution. And accordingly, that job is not able to signal to the game thread the completion of the anim jobs. So even though each individual operation here, Wise and game engine work, is still taking the same number of CPU cycles, because of this thread misschedule, Wise's audio work has now caused the main thread to miss its deadline by a significant amount, likely resulting in a dropped frame, which we don't want for the game and user experience. This is probably a familiar problem to many developers by now, and a plethora of solutions have been taken to address this. The easiest one is just to let Wise run on its own core all by itself, but this has the downside of the game having one less worker thread to play with. The game's frame times have stabilized, but the peak throughput has been reduced by up to 15% because of that lack of a worker thread. Another solution we've heard of is to modify Wise to try and launch jobs on the game engine worker threads when running the Audiokinetic, but this requires a lot of sound engine divergence, which then makes future upgrades harder to integrate into the game. One other one is maybe the L engine thread is disabled and the game attempts to call render audio manually. But this requires other very tight performance constraints or other difficulties with scheduling audio um, that just makes things a bit harder to deal with. Or, of course, it's not a problem that developers have the time or resources to properly identify and resolve. The game just ships, and among other things, consumer feedback is just the game feels really rough, or it has a really uneven frame rate, and it's just really choppy or stuttery and stuff. Like, I don't know, just that kind of response might be what comes up because of this problem. So we are now providing a solution for this problem in Wise, and that is a worker function callback. In the AK init settings, there's a new structure, AK job manager settings, which includes a new callback that a developer can specify. This new callback, FN request job worker, will occasionally be called by Wise when it has work to do. The first parameter in this callback is another function pointer that Wise provides for you to call, which is FN job worker. When FN request job worker is called, Wise only needs one thing: for the FN job worker function to be called in return. It can happen anytime, anywhere. Obviously, the sooner the better, but it can be scheduled and run anywhere it needs to be. Most notably, FN job worker can be called inside of a game engine job. In this way, this allows for the Wise work to be scheduled more cooperatively with the game engine. For example, this request for a Wise worker probably came in while the pre-fizz anim jobs were running, and the game scheduled it to run after those anim jobs had finished. This allows Wise work to be far less obtrusive to your game's execution, allowing for more stable game performance without relying on custom divergences to Wise. But Wise is still in the way of post-fizz anim job a bit, isn't it? Like, post-fizz anim job is the really important work for the game thread, and there's plenty of time afterward for the Wise job to run after that's done, right? Like, the CPU timeline has plenty of time available. Wise is running way ahead of schedule. Well, when you call FN job worker, one of the parameters you can specify is approximately how long the worker will run for in some number of microseconds. During the sound engine execution, Wise will occasionally check at certain points how long it has been running for. Once the worker has passed that stated deadline, Wise will reissue a new request for another worker so that work can be resumed later and then return back to the game engine. This allows the Wise worker function to terminate before the entire sound engine tick has completed, perhaps letting the high priority postfizz anim job start its work a little bit earlier than it would otherwise. Of course, this is somewhat ideal, but on average, in this kind of scenario, it may provide a net benefit. This may be something that is worth considering when finalizing what your game's CPU timeline looks like and how certain jobs are prioritized and scheduled. This is only part of the story with this new worker function, though. I mean, we added a new structure called AK Job Manager Settings, but they're not settings for your jobs. In conjunction with this, we're also looking to improve Wise's usage of parallelism and concurrency on modern CPUs. For Wwise 2022.1, we have also internally developed our own task graph scheduler, i.e., the AK Job Manager, to handle multi core processing. This replaces the old Parallel 4 functionality Wwise used to have. Once you have set up the worker request function to run on your systems, there should be little extra work required to go even wider on the CPU. For the most part, it should just be setting U max active workers to a value greater than 1. With the old Parallel 4 functionality, during processing of the bus graph, of which this is an example from a shipping production title, Wise was limited in what parallelism it could achieve because there was little ability to express concurrency in the operations being run. For example, during execution of the bus graph, the only portions where Wise could go wide was when executing each level of the graph in parallel, but it couldn't execute different levels of the graph concurrent to other levels as well. Now, though, Wise can go much wider in the execution by being able to execute work in the bus graph as soon as all input tasks have completed. Moreover, Wise can attain far greater concurrency than before. For example, if the couple buses in the sample graph, highlighted in blue here, take a long amount of time to process, maybe they're doing some complex multi-channel convolution effect, then these buses highlighted in orange are the ones that Wise can execute concurrently to those two. If most of these in orange are very simple buses, such as simple stereo buses with some EQs and compressors, then they will be executed much more quickly than the buses highlighted in blue. The newer job manager execution should let those buses in blue start execution much sooner and allow other work in the graph to execute sooner as well, reducing the total wall clock time of the bus graph processing. One other thing we kept in mind when designing the new job manager and worker request system was to greatly reduce or keep under control the number of jobs that Wise requests back to the game engine. Our internal job system was carefully designed and tuned to have very little overhead, even when each job takes only 10 to 20 microseconds to execute. But we understand that larger scale job systems for full games can be more heavyweight, mostly due to being far more featureful than what our job system needs to deal with. For example, some game engine job systems may target an average execution time of 500 to 1,000 microseconds per job in order to keep the overhead of their job system to a minimum. If Wise issued worker requests for each of its jobs individually, it could absolutely swamp many game engines. By having worker functions run many jobs in sequence, jobs of our own rather, literally until there is no more work to be done at the time or the execution time limit has been hit, and by only having new worker requests be issued when Wise actually has work to be done, up to the limit specified in the job manager settings, Wise is able to mitigate this overhead significantly. For example, this simple setup from an internal test has 23 jobs scheduled internally, but with max active workers set to 3, Wise only ever issued 4 worker requests. In this case, Wise goes wider during the software voice phase of execution, but the bus graph in this example was too narrow to have 3 workers running concurrently, So only one extra request is made during that phase of execution. Then, after the bus tasks are complete, Wwise will roll right into the epilogue of the sound engine tick. So to wrap up, while Parallel 4 did provide some benefits for some developers, it was fairly limited in what it could do. Its peak throughput was very constrained and required the game engine to schedule many jobs, and jobs still had to be run very imminently for the benefits to be effective. Now, we feel that the new job manager should be much more effective for more developers. It has much higher throughput, much improved latency, and issues far fewer requests for game engine jobs than before. Going back to the previous CPU scheduling example, let's consider that Wwise has been configured for more parallelism. Something like this may be more achievable. Where the game has configured Wwise to run on more threads, Wwise is not able Wwise is able to finish its work faster and configure. Sorry, let me try that again. Where the game has configured Wwise to run on more threads, Wwise is now able to finish its work faster and configured to not have to intrude on other time-critical work for the game. We think that this will allow developers to more effectively use the compute resources of modern multi-core CPUs to attain better performance for the sound engine as well as their game as a whole.
That's incredible stuff. And
Thank you.
it is all the way down the rabbit hole of microsecond precision that you're talking about to kind of bring this thing into the modern era of development. Excellent overview. And you know, it really illustrates just how far we're going to try to retain the kind of performance that's demanded by today's modern experiences, right? And Wwise being able to,
especially with like game frame time stability. Like I think a lot of people like Digital Foundry is really exceptional in this regard and really pushing on. Yes, like every dropped frame that they measure is reported, and so being able to avoid its individual dropped frames can really help out with just the overall game feel, but also helping the presentation and that kind of technical review. Yeah.
absolutely. So again, being able to go wide with this processing and scheduling is a benefit to games that are there to wrestle all of the power out of today's modern platforms, as well as getting the most out of other platforms that might not be as powerful. So it's a
Yeah.
across the board improvement to the way that Wwise can work with your production. So awesome.
Yeah, even for like I mentioned before, mobile CPUs benefit from LPF and HPF processing. They might also benefit from being able to run Wwise on more cores. Again, mobile may be able to because it means that they can the CPU can race to zero faster and therefore use less power on the CPU by letting the cores get back to sleep faster than it would otherwise. Yeah, this can have a lot of benefits in a lot of areas.
Yeah. I think it's great to be shining a light on the work being done by the core team at Audiokinetic in these areas because it might go unnoticed by some folks who are just accessing Wwise through authoring application, and that's okay too, right? At the same time, it's good to be pushing along with the rest of technology at the edge to make things feel good and performant.
So before we finish, I'd like to wrap up with some other tips for leveraging this new functionality. First, we strongly recommend not to naively max out how many workers you can use at a time, as fun as that idea may be. For one, launching workers is not a free operation, so issuing more worker requests can actually be used may result in a slight loss of CPU time. As well, the entire sound engine is not massively parallel. Amdahl's law is absolutely a major factor, a limiting factor here. And lastly, launching more workers or initializing more worker threads to be able to run Wwise jobs may require more memory due to extra thread local heaps and caches. In the near term, this would be a minor waste of memory, but in the long term, on PC, for example, this could result in other stability issues if your game on Wise is in the future running on some 128 core CPU and you've just configured the job manager to run on 128 workers. It may be that simply having a max of 3 or 4 workers is all you need, and that can still give a significant benefit. If that's what works, then just leave it at that number. Next, one thing I'm sure some people have heard, or heaven forbid, said: we have next gen CPUs now, so performance is not an issue, right? Only to find a few years later, they're staring down a fully loaded CPU timeline again. As is always the case, even on the new current gen consoles, I urge you not to fall into this trap, even if it feels like you have a lot of room today. Just because the tools are available to run audio across multiple cores does not mean that you suddenly have unlimited CPU time at your disposal. We've seen some game teams already start to max out the CPU on current gen consoles, so improvements that affect total CPU time are still valuable, and that includes reductions to audio CPU time as well. As well, one thing that is worth considering when balancing Wise execution with game engine execution is if audio has to be executed at a time critical priority level. The example timelines shown before demonstrated how there can be some value in letting other work that is time critical run in favor of audio. So maybe one reason to use multi-core processing is to let audio be a bit lazier. It may be desirable to let time critical game engine work finish earlier, and then audio work is treated as a normal or high priority job that can fill in other bubbles on the CPU timeline. For example, if you're running Wise at the stock setting of 512 samples per frame, that means the sound engine is running at only 94 hertz. If your game is targeting video render rates of 120 hertz or higher, then that is probably the more important performance target to hit and maybe should be a higher priority on the CPU. Similarly, maybe you can use the extra CPU resources to lower the amount of audio latency Wise works with in software just because the audio updates can complete faster. Our default settings, again, are 512 samples per frame and initializing system output devices with 4 frames worth of data. This gives a total software latency of 2000 samples of buffered data, which is about 42 milliseconds of latency at 48 kilohertz. However, given that games are targeting 60 or 120 hertz for video, they can hit less than 35 milliseconds of latency, and it may be that audio starts to run slightly behind. And of course, this is putting aside other audio latency concerns due to streaming environments or 3D audio processing. So, if audio can complete more quickly due to the use of multi-core, perhaps it's worth checking to see if these numbers can be lowered. Like maybe you can lower the samples per frame because your audio wall time is lower. Of course, at 512 samples per second, at 512 samples per frame, you only really need to complete all the work in about 10 milliseconds. Otherwise, maybe you can reduce the number of refills in voice because any spikes that you have in the audio frame time can be recovered from faster and therefore hurt a bit less. So that's one other option that might be available for multi-core use going forward. Next, we'd recommend trying to manage the affinities of job workers carefully where you can, and if you have the time for that kind of balancing. The biggest thing that we would underline is to try and keep workers for Wise on the same CPU cluster or core complex. We synchronize some state across cores, and having to share data across core complexes can slow things down just a bit. If you can avoid it, it's good to have. Another subtle thing is that for systems that support simultaneous multi-threading, it may be desirable to only run audio jobs on one of the 2 hardware threads of a single core at one time. Some portions of our audio processing can be very heavy on floating point work, and it might be preferable to try and run audio jobs on separate cores so that we're not competing over those floating point execution unit resources, especially if you have many other jobs that you know are much lighter on floating point workloads. Also, for CPUs that have heterogeneous or asymmetric cores, such as Intel's Alder Lake or Raptor Lake CPU, or Apple's CPUs, where they have separate performance cores and efficiency cores, if you have worker threads designated for P cores specifically, it may be desirable to run audio there and not on the E cores. P cores can offer disproportionately higher floating point throughput and let us wrap up our work much sooner than we might otherwise. And lastly, this is a small tip, but it is worth noting in case of any uncertainty. Some game engines need memory for their job systems or some other set of resources to be created or reserved upfront. So you may be wondering how many worker requests may be in flight at once, especially since we request jobs at an unpredictable basis and rate. The max number of worker requests that might be issued is not strictly the max number of workers that Wwise is initialized with. Rather, it is double that number. This is because theoretically, each worker may be simultaneously in a state where it is requesting a new worker while already running a worker that is about to retire. So that's something to keep in mind if your game engine job system is built with this in mind. So to wrap up, the Wwise 2022.1 preview already has all of the core job and profiler functionality in the SDK. You can get it today and start experimenting, or at the very least, verify behavior in your systems and custom plugins. To come forward in Wwise 2022.1.1, that will incorporate some further performance improvements, some of which was shown in this presentation, such as setting up the entire audio frame to run your worker functions, not just the voice and bus processing. We're also going to be eliminating many temporary allocations we make in the engine and some of our supported plugins. And we're also going to be fixing some critical sections that some of our parallelized jobs can still acquire, which can radically slow things down in some circumstances. For example, if you're running a lot of I/O streams, there's some contention on critical sections there. Or if you are playing sounds from events that requested get source play position support, there might be some contention there across multiple cores that we're looking to address, either in .1 or that might slip into .1.2. Also, the Unreal integration for Wwise 2022.1 will implement support for these worker functions, which you will be able to configure in your project's initialization settings. On the right is a screenshot from Unreal's Timing Insights profiler.
And we'll be right back with David in just a second as he summarizes what is in the box for 22.1 performance improvements. So stand by. We'll get him back into the stream here in just a second. This has been a really fascinating and deep dive into what's happening at Runtime, and I'm hoping that folks are getting some value. If you want to drop questions into the chat, we'll have some time to address those here at the end of the stream. And also, at any point, let us know feedback. As David mentioned, we've got the beta and public preview out there in the world right now. You can grab it and put your hands on it. Dig through the SDK. Look for opportunities in your pipeline to test this functionality out and provide us some feedback. That's what this preview and beta phase is all about. And of course, we're leading up to an exciting fall here with the full release of Wwise 22.1. I'll mention again, next Wednesday, October 12th at 2 o'clock Eastern, 11 Pacific, we'll be hosting the Wwise Worldwide Online Expo. This is a chance for us to give you a a deeper look into some of the features coming into Wwise 22.1. And so this will be part product, and we'll also have a exciting Audiokinetic product reveal. So we're encouraging you to tune in for that and get registered. We'll drop in the link to registration into the description for this live stream and video, and it's in the chat there for folks who are here with us today. And so I'm going to transition back to having our special guest today, David Crooks, in the live stream. Welcome back, David. Good to have you.
Can you hear me okay?
Yeah, you're doing great. And we're just getting the wrap up and lost you right as you were explaining some of that Unreal excitement that's coming down the pipe.
Yeah, so, sorry for the interruption. Like, a computer couldn't have died just 5 minutes later. Anyway,
smooth.
I'll start where I left
off.
Cool.
Cool.
So the Unreal integration for Wwise 2022.1 will implement support for the Wwise worker functions, which you will be able to configure in your project's initialization settings. On the right is a screenshot from Unreal's Timing Insights profiler, showing not just the Wwise jobs running on Unreal's worker threads, but also demonstrating some of the detailed profiling data now available inside of Timing Insights itself. Lastly, I'll note that while we have only jobified the event manager so far, we're aware that, like, for some people, that bank manager is still a problem, but for now, that is still behaving the same as it was before. Performance issues with it are definitely something that we're aware of and want to resolve sooner rather than later, though. They will keep you posted on that for sure. So that's it for now. If you want to review other information on the Job Manager system, we have an article in the Wwise SDK documentation under Going Further and Optimizing CPU Usage. As well, feedback after release is always appreciated. I know Damien says that a lot, but it genuinely is. We do listen. In particular, CPU captures, platform-specific CPU captures can be very helpful, both for validation of past decisions, but also inform future decisions and future developments. Crucially, we won't know about problems you're experiencing unless you tell us about them. And even this matters because even if you don't require a fix for some issue in order to ship your game, it is still worth noting that you did run into an issue, because then it is something that we can look into fixing for the future. So that's it. So thank you very much for your time. And that
was excellent summary of what's waiting for people in the full release of 22.1 coming this fall, but also what's there right now, as you illustrated. We had a question come in through the chat. Will the Unreal integration allow the Unreal task graph to manage the Wwise jobs, or will Rise run a separate task graph?
So the question to that is, I technically the question is both, but realistically it's like we are issuing jobs on Unreal's task graph. Like, this is Unreal worker threads running Wwise jobs as far as it's concerned. So yeah, although the reason why I say yes to both is technically internally we're running a separate task graph, but we do not expose any details of that to the SDK integration. The only thing that an SDK integration or the Unreal integration needs to worry about is we have requested some time, some CPU time, call this function, and that's it. That's all that the SDK sees and has to worry about. Nothing else besides that. Yeah, like trying to minimize how much work is it's actually like less work than what is required right now for issuing parallel for tasks. That was definitely one of the key design considerations. Is we want to be able to have these jobs be issued and not expose anything about the job dependencies to a game engine, because a game engine may not represent job dependencies in that way, or they may not do it at all. So we solve it for ourselves, and we try and tune for our problems specifically, and then we try to minimize how much outside interface we have in that regard. So hopefully that answers your question.
Yeah, that was a great wrap up for that, and I again, value having your perspective here as part of the Wise Up on Air hands-on. We do our best to try and surface all the cool stuff that is happening here at Audiokinetic, and it's a gift to be able to involve developers who are working hard to make Wise great here to the community and bring these things to the surface. So, and that was a really deep dive all the way to the bottom in order to carry that up to the top, David. And so thank you so much for bringing your experience and expertise today. Nice work. Cool.
Okay.
Well,
if no one else has any questions, then
it was I think a beautiful pitch to hit this afternoon. I thanks so much for your time. We're getting some thanks coming into the chat, and I know that this will be available for replay, and folks will get a lot of value out of it in the future. So thanks so much. Looking forward to launch, and we'll see the rest of you folks at the Wise Worldwide Online Expo next week, October 12th, 2 p.m. Eastern Time. David, until next time, thanks so much.